I will give you a floor.
Okay, thank you. Thank you. Good afternoon, ladies and gentlemen. My name is Francis Balestra from National Center for Scientific Research in France, from European Cellular Institute and also Grenoble Institute of Technology. I am very pleased to moderate this session with Professor Ken Uchida from University of Tokyo. We will have also today some presentation from some of our experts in the cluster 4 of INPACE dedicated to semiconductor. We have some presentation of Professor Mitsumasa Koyanagi from Tokyo University, Professor Jehyung Kim from UNIS, Professor Tae-Young Park from Gasho University, Professor Joon-Kyu Han from Soga University, and Dr. Giorgos Fagas from Tyndall National Institute in Ireland. So our cluster is dedicated to enabling technology for the chips for the future. So we need technology for artificial intelligence, for IoT, for communication network. And so we are going to discuss now the technology needed for all the electronic system and communication. So I want to start with this slide. What is the aim of our session is to discuss the challenge and possible solution for the main area of chips for the future, which are the so-called more area, more than more, beyond CMOS, novel computing architecture, heterogeneous integration and packaging, and sustainable electronics. I would like to say that all these topics are included in the digital partnership for semiconductor, with a digital partnership with Japan, South Korea, and Singapore, and also with Trade and Technology Council with India. And so we will discuss opportunity for international cooperation. We have to say also that this cooperation is very important for many purposes. For speeding up technological innovation, for avoiding duplicative research, and for strengthening value chain, because there isn't any region in the world we can manage all the semiconductor value chain, which is very complex, and we need international cooperation. And also, we can add that it's now the right time to strengthen international cooperation, which is supported by different CHIP Act and the new semiconductor strategy in many leading semiconductor countries. Just to mention that the cluster 4 so is one of the 5 clusters of INPACE, but you already know that. Now, I would like to start with this short introduction, the more challenge and possible solution. So in the more activity, we have many challenges dedicated to the transistor architecture, with so-called power, performance, area, cost challenge. We are facing memory walls, power wall, and sustainable electronics, which is sustainable manufacturing, which is becoming a very important field, taking into account energy consumption, material consumption, gases consumption, and also the life cycle analysis. We need to find solutions for sustainable electronics. Just to mention some data, we will reach very soon 1 zettabyte global data generation, which is a very huge problem. So due to many sensors, to the contribution of human, but also of machine in the future. Looking at the energy consumption for machine learning, computing needs in the future, we can see that the last year, due to deep learning era, we have doubling needs of computing effort every something like 6 months. So it is a very important domain also for the future. Looking at the worldwide energy production, if we don't do anything, we will take into account the computation needs, communication needs for energy. We will reach the worldwide energy production by the middle of this century. For sure, we need some solution to reduce the energy consumption of electronic system. What are the solutions? We have different kinds of solutions. So we have to reduce by a factor something 1,000 the energy consumption in the next decade, using transistor scaling, novel memory technology, disruptive computing architecture, and the so-called 3D integration with chiplet. And all these different possible challenge solutions will be presented by my colleagues this afternoon. just some roadmap for future computer system. We need to combine novel material, new device architecture, novel interconnects, integration of photonics also, and novel computing architecture in order to continue to improve performance and at the same time reducing energy consumption. This is, for instance, the roadmap for transistor architecture, moving from different technology with different device architecture, and using silicon, a very thin film, but also using novel material like 3D material in the future, which is non-silicon, but maybe will be needed at the end of the roadmap. This is some example of memory technology. In addition to transistor architecture, we need new memory architecture to reduce power consumption, but also to have better reliability and better performance. So, for instance, this is a very important area, the so-called non-charge-based memory, which will be needed, which are resistive memory or capacity memory, which will be needed in the future for electronic system. Another very important field is the 3D-dimensional integration. Up to now, we have had mainly 2D-dimensional integration, and so in the future, due to the many challenges we're facing, we need this integration in the third dimension, which started already for memory some years ago. We need it for transistor in the near future. Looking now at the global integration, we have two possible integrations. The monolithic integration, which was the starting point, I would say, of microelectronics, and we can integrate in the future more than 1 billion transistors, but we'll need more and more heterogeneous integration with advanced packaging, for which, with the so-called 3D system, it could be possible to integrate more than 1 trillion transistors in the future. This is a list of possible possible solution and collaboration opportunity at the international level between Europe and Indo-Pacific. I'm not going to give you all the list, but just to mention that these are very important topics for the future, for which international collaboration will be needed to speed up technological innovation and also to find some solution for the sustainability of electronics, as I mentioned. So it's combined innovation at the material level, device architecture level, interconnect level, including transistor and memory, also the 3D integration and new equipment like INA, EV, EUV lithography, which will be needed in the future. And so we can cooperate on all these topics using different tools. What are the tools? So this is the main list of the tools we discussed with our INPACE expert in the Europe and Indo-Pacific country. We discussed this for this symposium, but also we have had some online discussion previously. We will organize a webinar for all these topics, workshop in Asia Pacific and EU, so this is one of the workshops. We already organized some workshop in Europe the last month. An important topic also is the contribution to regional and international roadmap, which is a very important also area for multilateral international cooperation. We need international roadmap for short, medium, and long term. We could develop for sure also together some R&D and innovation cooperation on topic of mutual interest. Propose position paper for future joint activity, which could be supported by the Indo-Pacific countries, organize international summer school for training activity, exchange of researchers, and other possibility for multilateral cooperation is standardization also, for which we need many new standards for emerging technology. So thank you very much for your attention. Maybe we can keep the question for the end. We are going to move now, after the more presentation, to the more presentation, which will be presented by Professor Ken Uchida from University of Tokyo. Please, Ken.
Okay, thank you very much. Okay, Francis, thank you very much for your kind introduction. I'm Ken Uchida from University of Tokyo, and I'm actually working as the leader in more than more technology in SDRJ. SDRJ is kind of Japanese local roadmap, which is strongly related with IRDS. Okay, let me introduce the more than Moore roadmap activities in Japan. And probably, as you know, more than Moore concept is firstly proposed by the researchers from EC or EU. And the concept is that, so we should add some values to LSI chip, which cannot be realized by simple scaling of transistors. Okay, so transistors can realize the RF applications and also logic application, memory applications, but sensing applications and power device applications and also energy harvesting, those key technologies or key functions cannot be realized by simple scaling. Therefore, the role of the more than Moore technology is that we should add some values which cannot be realized by simple scaling of transistors. Okay, and presently, IRDS roadmap, more than Moore technology were categorized into 4 groups. And one is the smart energy, and which is basically the power electronics, and flexible printable wearable electronics, and smart sensor, and energy harvesters. And in terms of the roadmap, it is important for us to mapping the technology on the single map. And this is probably the common mapping of the power devices. We have the output power in the vertical axis, and the horizontal axis we have the operating frequency. And usually gallium nitride is located at higher operating frequency regions, and silicon carbide is located in the high output power regions. And of course, we should map the silicon technology also. And still, at this moment, we do not have a technology map which includes the new wideband gap materials like gallium oxide and aluminum nitride. But in future, we should map these new wideband gap materials onto the single map. And also, other important point is that, of course, the operating frequency and output power is quite important, but in some cases, output resistance is very important for some market applications. And also cost of the wafer is also quite important. The timing for the commercialization is mainly determined by cost or output resistance nowadays. Therefore, we should consider about what kind of vertical axis or horizontal axis should be appropriate for accurate mapping of the technologies. This is kind of wideband gap materials or smart energy applications benchmarking. And another technology is printed, flexible, and wearable electronics. And the background is that advancements in IoT and digital technologies have necessitated a wide variety of electronics technologies in living space. And the present status of flexible electronics is that, and already in flexible printed electronic technology is intensifying worldwide to realize low-cost electronics that can be deployed on a variety of surfaces, including living organisms and skin. Okay? And therefore, printed flexible electronics is fascinating to apply to the surface of skins or surface of living creatures. However, the reliability of the flexible or wearable electronics is still a big issue. Therefore, in road mapping groups in Japan, we consider that important trend is that flexible printed technology should be hybridized with silicon technology with small size, because the small size silicon chips can be integrated in the flexible substrate, and information technology or high-speed information should be treated with the silicon technology, whereas the flexible and printed technology offers us the function to monitor the signals from the creatures on the surfaces. Okay, so therefore, we consider that important trends for the flexible electronics for a sensor application is we should have the fusion of flexible technology and silicon technology. Hybrid electronics could be important. And another technology is the smart sensors. Of course, smart sensors are already integrated into the cars and plays an important role for the smart cars. But those radar and also accelerometer, those kind of sensors are already commercialized, and many companies pursue based on their strategies. However, chemical sensors have not been implemented into the society. Therefore, we consider that in IRDS road mapping, we should monitor or we should track the development of smart sensor technologies. And in case of the chemical sensors, we should have some good technology drivers to drive the technology of chemical sensors. And probably the potential sensors for activity monitoring, for example, myoelectric, electrocardiogram, those are quite important technology drivers. And also blood sensors and gas sensors for breast diagnosis could be next technology driver. But we should find some good technology drivers for smart sensors. And also demands from the application fields is very strong, particularly wireless and low cost. And also at the same time, we should realize the high accuracy and high durability. Those are very important demands from the application fields. But at the same time, it is quite difficult challenges for us. And major technical issue is always the accurate measurement according to the international standards. Of course, smart sensors fabricated by LSI technology could be very small and could be low energy and low cost. But we consider that the accuracy of the sensors should be very, very high. Otherwise, the sensors will not be utilized in real applications. Therefore, the major technical issues for the smart sensors should be the accurate measurement, and which should be in accordance with the international standards. And technical parameters, performance evaluation indicators could be these one, long-term stability and measurement accuracy, responsiveness. But of course, these are quite difficult to be achieved at the same time. Okay, now the final topic is the energy harvesting. But energy harvesting, these are the key contributors to the more energy harvester sections. And there are a wide variety of energy harvesters. And we have mapped the researchers in energy harvesting areas. And in Europe, there are many active research groups. And in Japan, also, we have some active research groups. And also, in other technologies, we have also active researchers in worldwide. But collaboration with these researchers worldwide could be quite important for energy harvester technologies. Okay. And this is the final slide. And more in STRJ, we have the smart energy section, and we are technology mapping is ongoing. And flexible printable wearable electronics are also ongoing. But hybridization or fusion of flexible electronics and silicon-based electronics could be important. And this section is very similar to the smart sensors. Therefore, in future, this section could be merged with smart sensor section. And smart sensors, identification of technology driver is most important. And we are now serving the healthcare applications. And demands for the application fields are not satisfied yet. Therefore, it is quite difficult for the smart sensors. We are achieving the low cost and also low cost and low energies, but at the same time, we have to realize the demands from the application fields. That is a big challenge. And thank you very much for your kind attention.
Thank you very much for this very nice overview. So after the more area, so including transistor architecture, memory architecture, the novel functionality, the more field which could be integrated in the future electronic system, we need also some long-term solution which could overcome some of the limitation of the device which have been presented up to now. And so this beyond CMOS field, the long-term field will be presented by Dr. Giorgos Fagas from Tyndall National Research Institute. Please, Giorgos.
Thank you, Francis, and good afternoon, everyone. My name is Giorgos Fagas. I'm based at Tyndall National Institute in Ireland. Tyndall actually is Ireland's research and technology organization on ICT hardware under the auspices of University College Cork and the government. And my role at Tyndall is actually dual. For quite some time, we've been involved heavily in European road mapping activities and developing several projects. But I'm also responsible for our CMOS++ program, which is looking at emerging materials, emerging devices, and architectures for information processing that interfaces with standard CMOS, right, and goes beyond CMOS into the future. So in this context, I'm quite happy really to introduce the Beyond CMOS ideas and key aspects for international cooperation. These have been mostly based on the International Roadmap for Devices and Systems, IRDS, but also in very strong interactions through various workshops and stakeholder engagements we had in the last couple of years in Europe. So what is Beyond CMOS? Beyond CMOS, at the basic level is something that will take us from what is now considered to be conventional technology in micro nano electronics, which is the standard CMOS, and it's going to be better in terms of efficiency and performance, maybe cost and environmental perspective into the future if we add this into the overall metrics. But it also has a relation with more than Moore. That's something we didn't mention, and I hope I'll make the connections. We didn't mention that yesterday, but I hope I'll make the connections. And it is based essentially in three aspects. It's based on the emerging materials, it's based on novel devices, and it's based on novel architecture. So some examples on the materials. So we have the 2D materials paradigm, where one can have really a new type of electronic device based on reconfigurability, changing various aspects like on real time, dynamically, the threshold voltage, the polarity of the current voltage characteristics, the sub-threshold slope, and all this that are important for basic devices. But also 2D materials apply to smart sensors and also on the flexible and wearable electronics. So that's a connection with the more than Moore domain. I forgot to get rid of this. Multiferroics is another example of materials where they could take us into the future for where we essentially marry the ferroelectric and the ferromagnetic properties of materials to have both of them at room temperature, and this can be used for really dense memories into the future, but also they can be used in neuromorphic computing architectures, which are more energy efficient, and then would address some of the issues that Francis mentioned earlier. But in general, there is a whole zoo of materials that can help us into the future addressing the challenges of power, performance, cost, possibly cost. That's a very big question. And environmental sustainability. And these are materials that are based on macroscopic quantum phenomena that one could see emerging from the materials themselves. And yeah, you can see the 2D materials already there, but there is also transition metal oxides, topological insulators, and various types of antiferromagnetic materials. Now, going into the future of devices, we have there we're still looking for the perfect switch. We don't have the perfect switch. In fact, we operate far further away from the perfect switch. The perfect switch should be, almost a step change there with the external drive, so that I can have something going from 0 to 1 with a very little external perturbation. That's the most energy efficient switch. And this can be used in both logic and memory. And there are several switches on the roadmap, some related with the CMOS extension, and already mentioned by Francis. Some that take us a little bit further out, try to improve a little bit these transfer characteristics. But there are also other solutions that are based not only on traditionally manipulating the charge, but also manipulating other types of excitations, or even the spin, or other types of excitations, macroscopic excitations into in the material or in the channel itself. Then we have another paradigm of a device which takes us beyond the switch, and that is the memory store, and that has significant applications in future data storage, in neuromorphic computing, but also in more than more domain, like true random generator, and also on the cybersecurity, by being able to generate what is called physical unclonable functions. Then there is another, I'll give you the slides, don't worry, okay? There is then another type of beyond CMOS technologies that they are looking at how the devices actually interact directly with the system architecture, and this is a completely different new paradigm of how we can build computing systems. And there are several such systems that are being discussed in the IRDS. One has already been mentioned, and probably we are going to hear a little bit more, which is around neuro-inspired systems, neuromorphic systems. Then we have dynamical systems, analog-based, probabilistic systems, reversibles, and a very one which is very close to neuromorphic, which has to do with digital in memory, processing near memory. But there is a completely different paradigm as well, which could allow us to solve problems not only more energy efficient, like the previous system architectures could do, but could also allow us to solve problems that we cannot currently solve, going beyond what is possible with classical computing. And this is the quantum computing. And there are several hardware realizations, qubit realizations, based on the superconducting junctions, based on spin manipulation in semiconductors, based on ion and neutral atom manipulation, using laser cooling. There is also the paradigm where we can use photons as the carriers of quantum information, and there we can also use what is called photonic integrated circuits, and we can go one step further in terms of scalability. Now, there is still a lot of work to do on that, right? So there is no one architecture that is ahead of the other. Each one of them have their advantages and disadvantages, but that is a very, very long discussion. I don't want to go down there. But the premise of Beyond CMOS is actually that it can work on several axes. It can work on the axis of reducing the energy per operation, so that we have more energy efficient devices. It can work on improving the overall architecture by adding additional complexity in terms of going in the architecture, going into non-von Neumann architectures, but also we can introduce a different kind of way of thinking where we might not use all the information, or we might start thinking about that we can do things in a more statistical manner when we actually don't need to solve the problem to infinite accuracy, and that will also address a lot on the energy efficient axis. There are many challenges and collaboration opportunities. Here I have 4 bullet points that have come out from, as I said, several workshops that we had organized within the Europe in various forums. But I think we need to work internationally on these long-term research projects. The challenges are immense, complex, and there is a lot of room at the bottom.
Thank you very much, Giorgos, for this very nice overview of the beyond CMOS field, the groundbreaking technology. So, thank you. So after we are planting the more Zalmo beyond CMOS area, now we are going to develop some new computing architecture which have been presented. We're going to strengthen a little bit this part of the presentation because this architecture will be very important, for instance, in the field of AI application or other one. And so we are going to have a talk now, the next thought by Professor Kim from UNIST is going to develop the roadmap for computing architectures of quantum computing architecture, especially using photonic ICs. Please.
Thank you for the introduction. My name is Jehyung Kim from UNIST, and in previous session we heard lots about the advances and concern about the AI technology. And I think the quantum information science and technology would be another one leading the future information science. So I think that Richard Feynman was the pioneer and also the one who proposed the quantum computer we may need. So actually to simulate this kind of molecule and even for small stuff, to calculate, to simulate, to expect precisely, we need to calculate those things at the quantum level. But for that, we may need machine operated by quantum mechanics. Oops. So for that ideas, lots of researchers developed the quantum machines, but we first needed while the classical computer developed scale up like this, but in quantum community, we first need to scale down. We need to go to D1. So first, we need to isolate single quantum particles, and we need to find a way to manipulate, read out their state. So we did, lots of the research group did with atoms, trapped ions, a single quantum dot, optically confined using the gate. So having these isolated quantum emitters and developing the way to manipulate, read out their state, then we can go now 2. So the 2-qubit gate is essential to make any information processings. So also we need to develop the 2-qubit gate with high fidelity and long coherence time. After that, lots of multiple physical platforms did all these things, and we are trying to do scale up, not 1 or 2, but 10 or 100 qubits. So you can find several the example like the neutral atom, trapped ions, superconductors, or quantum dot, defect in crystal, and photons as well. So this is a nice thing. So all these different physical platforms doing race together. So among them, we like to do these things using the optics. So for quantum photonics, we need a source of quantum light. The quantum emitter like atoms or ions, they can provide the single photon sources. And also we may need lenses. So all these lenses systems, and we can do lots of quantum optics experiments. But eventually, we will not want to use this kind of the platform, but eventually we may want to integrate all the things in our circuits. So the photonic integrated circuits can generate a single quantum light and also can manipulate all these quantum lights. So eventually what we want to do in all integrated quantum systems, we need integrate multiple quantum light sources, and we also need manipulate these directions or polarizations or light matter interaction in a circuit. And also one important part is reading out the single photon in a circuit. To achieve these things, we need very high. There are several challenges exist all these techniques. First, we need very highly efficient single photon sources and detectors. That is because we are encoding all the information at the level of single photons. If we lose single photons, we lose everything. So we should keep the high efficiency for all the detectors. And even in the waveguide, we should not lose the single photons. And also, we need to the proper technology to integrate and interface all these different parts with high efficiencies. And also, we need to scale up not just single photon or two photons. We may need multiple, a few tens of single photon sources. So we need to scale up the system. Also, we need to integrate multiple detectors as well. And eventually, we may need error corrections. So eventually, we will lose single photons. So we need to find a way how to correct such single photon loss or such errors. So we need to develop some scheme or model for correcting all these errors. So in that sense, we still have lots of challenges in this field, and then so that is why we need multidisciplinary international collaborations. So like from the quantum resources, we need more higher efficiency single photon sources and detectors, and we may need better algorithms and protocols for error corrections or quantum algorithms. And also we need better technologies for integration and interfacing all these small parties. And eventually we need to develop this kind of quantum systems. So including Korea, there are lots of good, excellent research group in EU. So there is a lot of chance to collaborate to each other. In particular, in Korea, there are lots of good groups. In our group, UNIS, we are developing highly efficient single photon sources, and we are studying the quantum light matter interactions, which could be useful for quantum information science. And there are lots of other groups who integrate the detectors or lasers in a circuit and developing functional quantum photonic devices and quantum photonic processors. And recently, the Korean government raising lots of funds for quantum technologies, and also we started to develop the quantum fabrication centers that would provide advanced nanofabrications, the industry infrastructures which is required for quantum science and technologies. So that's it.
Thank you very much for this very good presentation about quantum computing architecture. So we are going to continue with novel computing architecture will be needed, as mentioned, for increasing performance or reducing power consumption in future electronic systems. So now we are going to have a presentation for neuromorphic computing by Professor Han, please, from Sogang University.
Thank you for introduction. I'm Joon-Kyu Han from Sogang University in Korea. I'm going to briefly summarize the roadmap challenges and solutions of current neuromorphic computing technology. And simply, neuromorphic computing is a technique that mimics the human brain in hardware to lower the energy consumption for AI. The current problem of conventional von Neumann computing is a large energy consumption because of the repetitively moving data between the processor and the memory. As the data that should be processed is increasing and the hyperscale AI such as ChatGPT emerges, this kind of problem is getting more severe. Also, the paradigm shift to on-device AI, which performs the AI function in the mobile or edge devices, needs low power consumption because of the battery issue. So new computing architecture is needed for mobile and edge devices, especially for the on-device AI. Neuromorphic computing technology is a new paradigm that mimics the human brain in hardware based on the fact that the human brain consumes only 20 watts of power while it performs very complex functions. So this table compares the human brain, the software-based deep learning using conventional von Neumann computing and hardware-based neuromorphic computing. Roughly, the neuromorphic computing has a million times higher energy efficiency compared to the software-based deep learning using von Neumann architecture. So to implement the neuromorphic computing hardware, neurons and synapses in human brain should be realized in hardware. So this is the roadmap of current neuromorphic computing technology. Since the memristor has been proposed in 2008, various kinds of synaptic devices were developed based on various memory devices. And in late 2010s, the artificial neuron devices were developed, and the integration technology of neuron and synaptic devices were developed to implement the entire neuromorphic hardware. And now the technology is focused on 3D integration to maximize the integration density and to increase the computing capability. This graph shows a comparison of neuromorphic hardware with other hardware such as CPU, GPU, and ASIC, which is typically the NPU, and FPGA. So neuromorphic hardware has low energy consumption, but it has low throughput due to the small number of integrated devices and the lack of system-level studies. And also, it has low accuracy to perform recognition like image and videos because of the limited device performance and the lack of suitable learning algorithms for neuromorphic computing. So I summarized some solutions for these challenges. To solve the low throughput issue, large-scale integration with high density is promising based on the vertical stacking. So vertical RRAM or vertical NAND flash memory is a typical structures of this vertical stacking. And also, the co-integration of neuromorphic devices and CMOS interface circuits can enhance the throughput by performing the system-level studies. To enhance increase the accuracy, various material or electrical engineering can be applied to enhance the linearity, symmetry, retention, endurance, and on-off ratio of neuromorphic devices. And also, algorithms like spike-based backpropagation learning can enhance the accuracy of neuromorphic computing. So this slide shows my own solution of these challenges, which is co-integration of CMOS-compatible neurons and neuron and synaptic devices. By mimicking the neurons and synaptic functions with a single MOSFET, it can increase the throughput by leveraging high integration density. And also, it allows the system-level studies through the co-integration with CMOS interface circuits because they are typically the MOSFETs, which are 100% compatible with CMOS technology. So this is the summary. Neuromorphic hardware can greatly reduce the energy consumption for AI, but there are some challenges such as low throughput and accuracy in current neuromorphic technology. So we need various kinds of engineering to overcome these challenges in terms of material, device circuit and system, or even in biological engineering. So worldwide collaboration between device circuit system engineers and biologists is essential to overcome the challenges of these challenges of neuromorphic hardware. Yeah, this is all of my presentation, and thank you for your attention.
Thank you very much for this very interesting presentation. Thank you about neuromorphic computing, one very interesting computing architecture for the future. Now we have seen different kind of material, device architecture, computer architecture, which we need in the future, but we need some kind of integration. And there are very promising technology for three-dimensional integration using advanced packaging, heterogeneous integration, for 3D system, for improving performance, improving power consumption, and also integration of future electronic systems. This presentation will be given by Professor Koyanagi from Tohoku University, please.
Thank you, Francis. I have been deeply involved in the semiconductor technology for almost a half century. And I firstly proposed 3D integration technology using a TSV around almost 30 years ago. I succeeded to fabricate the first 3D stacked image sensor and 3D stacked DRAM like HBM and the 3D stacked microprocessor around the year 2000. Okay. And at that time, I believed, okay, and eventually the majority of the IC chip will be occupied by 3D chip. Okay. So to facilitate the advent of the 3D chip era, it is very important to provide the 3D prototype 3D chip to people in the semiconductor area. And to do this, I constructed the 12-inch 3D production line in Tohoku University at the year 2013, okay, almost 10 years ago. I named this facility GINTI. GINTI stands for Global Integration Initiative. And GINTI is a kind of the consortium between the Tohoku University and the startup company, Tohoku Microtech. And the Tohoku University is responsible for the research and development. And the Tohoku Microtech is responsible for the production and business. Okay. So I'd like to briefly introduce our GINTI facility. Sorry. Yeah, quick.
Video. Sorry. This one. You need to.
Yeah, directly. Okay.
We will now introduce you to the clean room and main equipment of Tohoku University's 3D Superchip LSI Prototype Production Fab, GINTI, which stands for Global Integration Initiative. At GINTI, we have various types of 12-inch wafer production equipment to produce 3D LSIs, such as deep silicon etcher, wafer aligner, wafer bonder, debonder, and chemical mechanical planarization machine. This is silicon deep reactive ion etching equipment. Using the Bosch process, it can create high aspect ratio, deep via holes in silicon to make through silicon biases. This is the silicon via created, which is 2 micrometer in diameter and 40 micrometer in depth. Next is a temporary wafer bonder. The main purpose of the equipment is to handle thinning silicon wafers, and it combines silicon and glass wafers using a heat-resistant adhesive. This is a bonded wafer created by bonding silicon and glass together. This is a grinder polisher. Coarse grinding, fine grinding, CMP, and final polishing are performed in chambers Z1, Z2, Z3, and Z4 respectively. This is an I-line stepper with infrared alignment function. It recognizes patterns on the reverse side of the wafers and creates fine patterns on the front side with extremely high precision. This is a wafer on the surface of which patterns are created with the IR alignment. Next one is a spattering machine for TSV. With its long throw structure, the spatter can create barrier layers and seal layers down to the bottom of deep silicon holes with high step coverage. This is a wafer debonder. It sticks a thinning silicon wafer which has temporarily bonded glass to dicing tape, peels off the glass wafer, and takes out the thin silicon wafer. This is a separated glass wafer, and this is a thinning silicon wafer. Next is a wafer aligner. It is capable of aligning wafers with each other at the precision of ±1 micrometer or less. Next is a wafer bonder. It can bond and stack wafers together in a vacuum with maximum load of 6 tons. This one is a flip chip bonder for chip-to-wafer stacking. It can pick up chips one by one from the dicing tape, flip them around, align them with the target location on the wafer, and perform thermal compression bonding. Like this, it can stack a large number of chips on the wafer. Next is a self-assembly multi-chip bonder. Using the surface tension of liquid as a driving force, it can simultaneously align a large number of chips to the wafer surface with high precision of within 1 micrometer and stack them. This is a multi-chip pickup plate for picking up a large number of chips simultaneously. Here, 500 chips are being picked up all at once. In the next process, the multi-chip pickup plate, which is vacuum sucking those many chips, is carried over to a position above a supporting substrate where liquid droplets are supplied. Then it is properly aligned, after which the vacuum on the multi-chip pickup plate is stopped, and the chips are released. As a result, as displayed here, it is capable of simultaneously aligning a large number of chips with high precision and stacking them. In addition to the equipment introduced so far, Joon-Kyu has various other types of equipment that is necessary for 3D LSI production. By producing and externally supplying various types of heterogeneous 3D LSIs using these production lines that are adaptive to 12-inch wafers, Joon-Kyu will strive to become an international R&D center for 3D LSI.
Now we are very interested in the new technology development, focus on the research and development of new 3D integration technology to enable 3D chiplet shuttle service. And another topic is the research and development of neuro-centric sensor system. Okay. And okay. To supply the 3D chip at a very low cost to the people, researcher in university or company, and it's very effective to fabricate the 3D prototype chip using the simple CMOS chip provided by semiconductor foundry, like a shuttle service. Okay, and chip is basically cheaper than the wafer. Okay, and usually people fabricate a 3D chip in the wafer level. So but the wafer level 3D integration cost is very high. So maybe university people can ask the 3D chip in the wafer level foundry. But if we use the shuttle chip, we can very cheaply fabricate the 3D chip. Okay. So we propose to new 3D integration technology for 3D chiplet shuttle service. Okay. And based on the reconfigured wire-to-wire bonding using self-assembly. So okay. Okay, anyway, many different kind of the chip, CMOS chip, provided by foundry. We aligned on the target wire self-assembly substrate using self-assembly. Then this is any kind of the chiplet assembled onto the substrate, then this using the self-assembly. So the alignment accuracy is very high, around 1 micron. Okay. Then this die is transferred to another support wafer. Then this chip sent from the back side. Usually the shuttle chip is a silicon thickness around 200 micrometer, something like that. But for 3D integration, we have to thin the silicon substrate down to the 50 micron. We simultaneously send the silicon chip down to the 50 micron like this. Okay. After that, we form the TSV like this. All kind of this is a chip-based TSV fabrication. Then stacked. Okay. Then eventually, you can very easily obtain the 3D stacked structure like this. Okay. Another our interesting topic is the neurocentric sensor system, and we integrated the 3D AI chip together with the various kind of sensor onto the silicon interposer. Of course, we need also 3D memory, and so that we are now developing kind of neuromorphic sensor system module, and also this sensor module, we can perform the personal or local learning also. But the major global learning is implemented by the AI control system or learning accelerator. We fabricated the 3D AI chip using a chip-based 3D integration technology like this. Here, the 4 chiplets integrated onto the silicon interposer. 2 neural chip and 2 memory chip, the 4 layer. Okay. And also the neural chips AI sensor fusion, the very important the edge application. So AI sensor, AI and the sensor fusion, the sensor chip output some future interaction data, okay, like this. This example is this one is the upper part of some kind of the sensor chip for image processing with future extraction output. The lower one is the voice signal recognition chip, also with a feature extraction function. Then this output is the input into the AI chip, transformer-based AI chip. So the main learning is performed by the FPGA system. Then we use that transfer learning to this chip. Okay? And so this chip can manipulate the various kind of the information, like voice information, the image information. Really large multi-modal model we introduced. And when I started the 3D integration technology, at that time I recognized the 3D integration technology, really system integration technology. So I started also various kind of the project related to the silicon photonics and circuit design and system design, and also the application of 3D to the bio area, like brain mass interface, something like that. The really much disciplinary technology necessary for 3D integration. So, as shown in this slide, we need various kind of knowledge and skill. So I understand that it is very difficult to cover all of this area in one research group. So I recognize now that it's very important to have international cooperation, and USA, of course Japan, the USA, and Asia, and especially in the EU, and through the INPACE project. So I'm expecting to have some collaboration with the EU through the INPACE. Thank you.
Thank you very much. Thank you very much for this great presentation of this very promising technology for 3D integration we needed in many electronic systems in the future. So now we have a last presentation with for emerging semiconductor which will be applied for security application. So this presentation will be given by Professor Park, who is working with Professor Yoo in Gashon University. Please.
Thank you for the kind introduction. So my name is Taeyeon Park, and I'm a research professor at Gachon University. I'm very honored to be here to participate the INPACE instead of my advisor, Professor Hocheon Yoo. So today I prepared a very short and very brief summary of the technology about the physically unclonable function devices. So the physically unclonable function, which is also called shortly in a PUP, so is some kind of hardware security device providing or possessing the random bit patterns such as like, these patterns. So we can use the PUP patterns for the digital security. So it should possess some uniqueness or randomness for each pattern. So we can evaluate the performance of the randomness of PUPs with the two indicators, which is called uniformity and interhaming distances. The uniformity is some kind of figure of merits possessing the ratio of the bit 0 and bit 1. And in the case of the interhaming distance, it is some kind of the factors evaluating unequal outputs for the unequal inputs of each device. So we can obtain these physically unclonable functions by using the conventional CMOS technologies. So for instance, we can use SRAM or DRAM or ring oscillators for obtain the or realize the PUP devices. But these devices, the silicon PUPs have advantages for the easy to integrate into the ICs. But there is some kind of issues because there are the silicon PUPs possess high process complexity, and we should induce the variation intentionally during the CMOS process because it's very perfect. The high quality process, so we should induce the variation intentionally. So to address these issues, we can use the emerging devices such as MEM listers. So by using the random filament formation process, we can get the PUP functions with the MEM lister arrays. And we can also use the other some random natures, such as we can also realize the PUPs by random doping effects on the conventional silicon wafers, or we can also consider the mixing of two substances and some kind of random nature such as Brown motions. So we can utilize the random growth of the nature of organic semiconductors. All random species can be turned to the PUP devices. And there's chances for global or joint cooperation. So there are issues about some PUP technology. The first one, for instance, the absence of the global standards. So there are no established standards for the PUP applications, and limited interoperability, so hampers security system compatibility. So and there are some also chance for, because of the rising of the AI, so there are machine learning attempts to model PUP response patterns. So there are need for complex PUP structures or multi-PUP systems. So we can develop efficient materials or manufacturing process together to address these issues. Thank you.
Many thanks for your presentation. Maybe we have time, 5 minutes question, maybe it's okay. So if you have any questions, I have some questions for the generic question, but if you have first of all some question for this presentation of the enabling technology for the chip for the future, for all the electronic application, AI, IoT, communication system. And maybe can I take just my first slide? Yeah, because I have some question.
This one?
Yeah. Thanks.
Which slide?
The last slide, yeah. Last one, please, again. Next one, yeah. No, it's okay. So, okay. So, if you don't have any questions, so I have some general question, very important for the semiconductor, for the chip of the future. Maybe I can ask my colleagues to answer one or several of these questions. So, some example, what are the priorities for international cooperation? Is it, first of all, roadmapping? We need roadmap in order to develop the technology, the equipment we need for the future. R&D cooperation on a special hot topic. Training also to the skill shortage problem, so you need some international cooperation for training. Multilateral cooperation for standard. Also, for the technology themselves, what are the priorities for the future technology? What are the biggest challenge for the chips of the future? And also, what are the main priorities for the sustainable electronics, Europe's sustainable electronic system? Maybe you can answer one of several of these questions. Maybe I can ask first of all Professor Uchida from Tokyo University.
Okay, thank you very much. So for the international collaborations, firstly, we need to identify the strengths of each area, right? So, for example, Europe has the FDSI technologies, and we may very much interested in the collaboration with Europe by using the FDSI. Therefore, the identification of the strengths of each area should be quite important. Mm-hmm. And also, to the competitive area, like as you said, 2D materials, we need to know deeply about that. Therefore, the pre-competitive area and promising materials, I think we can have very good collaborations. But of course, in terms of the future of the chips, we need to have some applications in our mind. So
yeah,
okay,
for sure. Okay, thank you very much for your comments. Maybe can give the mic to Giorgos, please.
Maybe I just add to that. I fully agree with what you said there. We need the, if I go back to yesterday's discussion, inspired, we need the one key action that is coming out from here. We need to sit down together and identify the complementarities and write that in a kind of a position paper that evolves into a roadmap for selected technologies. 2D materials could be one of them. Okay. Now, I'm not going to fall into the trap and answer the second question, no, because
as you want.
What are the priorities for future technologies? This depends on the country to country.
For sure,
well,
yeah.
Right. So, but I think if I look at international cooperation, I would take this as a key action.
Okay, thank you very much, Giorgos. Please, moving to Professor Koyanagi, please.
Okay, every item is very important for international cooperation, but as I said, the future semiconductor technology, the system integration technology, so we need a lot of the knowledge and skill, okay, and also the very wide range of area. So that it's very difficult to cover all this area in a small group, okay, one group or one country. So the around research and development is very important for especially international cooperation in the research and development. That is the most important area.
Thank you very much. So maybe, please, if you have some comments.
Yeah, those international cooperation is really important. So And I think the priorities for future technologies, I think all of the topics we present in today is all important, and you organized this session very well, so thank you. And I think each country has each strength in each technology, so I think this collaboration is very important. Yeah.
Okay, thank you very much. So, another comments?
Okay, maybe I'd like to comment about what are the priorities for the sustainable electronics.
Yeah.
So, similar to the first question, I think it will be the road mapping will be the priorities for the sustainable electronics, because in this case we should gather our some kind of willingness for some sustainable electronics or some developing some future technologies. So at this point of view, so maybe we should check or develop some roadmaps as the first.
Yeah.
Thank you.
Thank you. Yeah, I fully agree. So maybe I have some comments. So, so road mapping, I would say, is the beginning, because we need some international roadmap to strengthen our cooperation. Road mapping is a multilateral cooperation, and we have an international roadmap for device and system, for instance, which started 2 decades ago with international technology roadmap for semiconductor, but now we are looking at the system roadmap, taking into account the system performance in order to develop special technology which will be needed for the system of the future, from short, medium, and long term. And so I think we have to strengthen international roadmapping, because in the current international roadmap, not all the leading semiconductor countries, I would say, are sufficiently involved. We have to strengthen our international cooperation in these international roadmap efforts, which are very important, not only to find some possible solution for future system, but also to look at especially the gaps in which we need some focus for international cooperation, or to speed up technological innovation and to prepare the equipment for the future will be needed by the industry also in the future. So the road mapping is very important. For sure, developing joint R&D, so this could be done in different frameworks, but especially for bilateral cooperation with John Cole, for instance, which have been the case, which will be the case with, for instance, South Korea and Europe. Training activity, I think, is a very important topic. Skill shortage, I think most of our countries, Europe and Indo-Pacific, are facing skill shortage. Will face, for instance, in Europe, in the semiconductor field, we will miss something like 60,000 students for the next decade. So I think we need some international cooperation with joint training, also for reskilling, for attracting students, and so I think the training skill shortage also could be solved with some international cooperation. Standard for the emerging technology, for sure, is also an important field. So the priority depends on the country, but we can find some, using this kind of workshop, we can develop the matchmaking and to find some common priority for which we could develop a joint project. So that's very important. And the last topic, sustainable electronics, so now it's a little included in international roadmap, but not too much. So we are discussing about water, energy, for instance, in the IRDS roadmap, which are for sure very important, but not too much on the material, the critical material which are needed for the electronic, for future system electronics. That's also a very important topic to work on the material level for new material, for improving the performance of the system, but also for the substitution of the materials, in order to find some, I would say, some material which would be needed for the long term, for also sustainable electronic and sustainable business also, because the material topic is very important. It's not too much taken into account up to now in the roadmap for international cooperation. So I think we are facing many challenges for which international cooperation will be a must to speed up all these, to find some solution for the future of our society. So thank you very much.